Okay, good morning. And we have a very small part to be covered in that truss now. Okay, we are left with the design of base plate, what has to be explained to you. But designing the entire truss members, you have to practice them. Okay, I hope you have gone through this problem and tried solving it. Unless and until if you don't practice, I cannot help you in any way. So here what we have is once that truss design is done, okay, so this is the design of base plate. Okay, so this is what the base plate and anchor boards have to be designed over here. So in the beginning I told you there were some reactions given. Okay, so I just taken these reactions. Okay, so what you have at the ends, that is over the support of the column, okay, at the ends of the truss, at this point at A and G, you have the reactions coming over here. Okay, so you have to design the proper base plate over there for these reactions. Okay, and also there may be uplift what will be there due to wind load, and to prevent the uplift or overturning of the truss, there should be proper anchoring arrangement. Okay, you should have a boards which will hold down that truss in position. So you need to design those bolts or the anchor bolts. So first is design of base plate. Okay, now this is a concrete column what has been considered here. Okay, so I cannot directly rest this truss on the concrete column here. Normally what happens is it will result in high bearing pressure. This angle section what will be there, the bottom tie member, if I place it directly over the column, so there may be crushing of the concrete at the edges. Okay, that concrete may crack over here at the edges. Okay, to prevent this and also to provide proper stability to the truss at the support, we need to have the base plate over there. Okay, so we have to design that base plate and the anchor bolts for holding this base plate in position. Okay, so that has to be designed. So first, if you take up the design of base plate, okay, so what we have is these are the reactions at A and G. We have a reaction of 80 kilonewtons, third reaction of 80 kilonewton. Okay, and the column size for this particular truss, okay, so it is having a column size of 300 by 300 mm. Okay, and also there is an uplift force. Okay, so at the same supports A and G, this is a downward reaction. What is given here is 180 kilonewton. It is a downward reaction. What is coming here? So uplift. This is a upward reaction. Okay, if at all if truss is trying to be being uplifted by the wind load, there will be a upward reaction or force that will be experienced over there. Okay, so this is a due to dead load 180 kilonewton, which will be in vertically downward direction. This is a force in upward direction due to the uplift that is experienced by the truss in any case. Okay, now this column is given 300 by 300 and grade of concrete has not been mentioned in the problem. So what I have done is I have assumed that to be M20 grade. It is assumed over here. If it is not mentioned, you can go with the assumption. So now what is the permissible bearing pressure? Okay, so this permissible bearing pressure is from our clause of IS 800 2007. If you go to clause 7.4, the permissible bearing pressure on the concrete should not exceed 0.6 times FCK, 0.6 times FCK. Okay, so in our case, it comes out as 0.6 into 20, which is 12 Newton per mm square. This is the bearing pressure allowable on the concrete. Keeping this permissible bearing pressure in mind, we have to decide the size of the base plate. That is the planned area of the base plate. What should be the length and breadth of the base plate? So whatever is the reaction here, 180 kilonewton, that divided by your bearing pressure. Okay, permissible bearing pressure on the concrete. So that will be giving you the area required. So here 180, the reaction into 10 raised to 3 newtons divided by 12 newton per mm square. Okay, so that is 15,000 mm square. This is the area of the base plate, what is required. If at all, if you want the stresses beneath the bearing plate to be below this 12 newton per mm square. Okay, so what we'll do is we'll adopt a base plate of size 200 by 200, a square base plate of size 200 by 200. So from that, what is the area we are going to provide here? It is 40,000 mm square. Required was 15,000 mm square. What we have provided is 40,000 mm square. That is more than sufficient. Okay, why it has to be increased is there will be boards which will be coming in that base plate. Okay, for that purpose also I require some size of the base plate to accommodate the boards. So I have chosen 200 by 200. But in any case, I cannot exceed this column size 300 by 300. What is given here? That cannot be exceeded. I cannot provide a base plate of 450 by 450, which is it is of no use. Providing such a large base plate larger than this column is of no use. Okay, so I have kept some offset of 10 mm over here or 50 mm on either size or either side of the column. With that, I have decided the size of our base plate. Okay, so this is a base plate. Now deciding the thickness of base plate, you don't have to go for doing the calculation for this, because the bearing pressure, whatever the upward pressure will be experienced by bearing plate, will be very less, since size itself what we have decided is 40,000 mm square, which is more than required. So here what we'll do is we'll provide a minimum thickness of bearing plate. Okay, you just mentioned a minimum thickness of 10 or 12 mm, okay, of this bearing plate. So what I have taken here is nominal thickness of 10 mm will be provided for the bearing plate. This hatched member, what you see here, that itself is our base plate or the bearing plate provided at the support. Over this truss will be resting. So what size I have decided is 200 by 200 size, and the thickness will be 10 mm. Okay, so either 10 or 12 is sufficient. That out of these two, any one thickness you provide that. Okay, and then this completes the size of the bearing plate. Okay, plan area is 200 by 200 and thickness is 10 thick. Okay, that is one part. What has to be decided on the support, one of the member bearing plate. Now, other than that, we have anchor bolts. Now, this bearing plate, what we decided was based on the downward force, this 1 kilonewton, 180 kilonewton force over here. Now, we also need to take care of this uplift over here, uplift force of 130 kilonewtons. Okay, so what you have to do is you need to uh, provide proper anchor bolts. Okay, these are the J bolts. At the end, so you'll find such J hooks. What you have, so they are mainly meant to have proper anchorage. So these bolts have to be provided here. So these anchor bolts will be based on what is the uplift force here. On that basis, we will decide the size of the anchor bolts. So if I adopt 20 diameter bolts, okay, I have used 20 diameter as the anchor bolt size here. Okay, 20 The class of bolts, I have taken the same class, 4.6 grade. Okay, so from this, what is the strength in tension? We also have design strength for these bolts under tension here. Okay, from IS 800 only, you will get those design tensile strength of the bolts. Till now, what we have seen where the uh, strength of the bolts under sharing and bearing. Okay, so these two strength we have checked over there. We already have dealt with them. We have only come across such strength under sharing, single share, double share, or in bearing. That is what we have used. But in this case, what is happening here is there is a direct tensile force that is being resisted by the bolts. So we have to decide what should be the size of the bolts based on that uh, direct tension. Okay, so the clause you'll find that, and in that you'll also see that you can calculate the design tensile strength of the bolts. Okay, tension capacity. This is the tensile capacity of the bolt. Okay, TDB, which is equal to TNB upon gamma MB. Okay, tension capacity of the bolts. Okay, so this capacity, what I have mentioned here, is calculated from this clause 10.3.5. Okay, TDB, which is equal to TNB upon gamma MB, and TNB is to be calculated from this expression 0.9 FUB and that should not exceed FYB into ASB into gamma MB upon gamma M naught. Okay, AN is the net area at the roots, 0.78 times the gross area. Okay, that is AN. ASB, the area at the shank portion of the bolt, which will be based on the nominal diameter or the gross diameter of the bolt, pi by 4 into whatever is the diameter of the bolt, that square. Okay, that is how ASB is calculated. Whereas AN will be net area, 0.78 times the gross area, 0.78 times this gross area here. FUB, ultimate tensile strength of the bolt, and FYB is the yield stress of the bolt. Okay, gamma MB and gamma M naught. Gamma MB will be 1.25, whether it is field fabrication or shop fabrication. Gamma MB, what we have seen, factor of safety for bolts, it is 1.25. Gamma M naught, factor of safety for yielding, it is 1.1. So this clause will help you in determining the tensile capacity of the bolt, the design strength of the bolt under tension. Okay, so I have taken that from the clause 10.3.5, page 76 here. Okay, tensile strength of the bolts, TDB, which is equal to TNB upon gamma MB, and in turn TNB will be 0.9 FUB EN, and you should see that it is less than FYB into ASB into gamma MB by gamma M naught. Okay, so AN 0.78 times the gross area. 0.78 into pi by 4 into 20 diameter is the bolts. So into 20 square. So this is the net area, 245 square. Area at the shank portion, simply pi by 4 into 20 square, this term, which is 314 square. Okay, so on substituting in that equation, okay, what we have, nominal tensile capacity comes out to be 85.63. Okay, so one term 0.9 FUB into AN, it is giving me 88.2, whereas this term on the right hand side, it is giving me a strength of 85.63 into 10 raised to 3 Newton. Out of these two, whatever is least, that is adopted. This value 0.9 FUB into AN is exceeding FYB ASB into gamma MB by gamma M naught. So this 85 FYB ASB into gamma MB by gamma M naught has been taken as TNB here. 85.63 kilonewtons is our TNB value. Okay, so on this basis, we have decided what is the design strength under tension for the bolts. Okay, for these bolts of 20 diameter. So it will be 85.63 divided by gamma MB 1.25. So it comes out to be 68.5 kilonewton. This is the strength under tension. Okay, is that clear? Like we did the calculation for strength of the bolt in sharing, single shear, double shear, and bearing. This is one more strength. What is there under direct tension? Okay, so that has been done over here, right? Because these bolts are subjected to direct tension, uplift, direct pull is there on these bolts. So I need to know what is the strength under direct tension for these bolts. So this is what the strength is, 68.5 kilonewtons. Now what number of bolts have to be provided? Whatever is the uplift force, okay, this 130 factored uplift force, 130 kilonewton, okay, so that divided by strength of bolt. So that is giving me 1.8 numbers. You require 1.8 volts. So I cannot provide that 1.8. What we'll do is we'll provide 4 volts, one at each corner of this base plate. 4 volts, minimum 4 volts have to be provided there. One at each corner of the board, this base plate. Sometimes you may come across more than 4. In that case, you can arrange them along this line on the edge of the base plate. So here we are providing minimum 4 numbers. Okay, so diameter of bolt 20 number of bolts 4, and also this length matters here. Okay, it should be having sufficient anchorage strength. So this length should be equal to development length over here, development length in tension. Okay, that is the development length what you calculate for the reinforcing bar, LD. Okay, on that basis it will be done. You just mentioned that length of the bolt should not be less than development length, just LD, not LDC, LD. Okay, length of the bolt. So that is the anchor bolt and the base plate design, what has to be done at the end of the truss design. So this is the one small part, that calculation what it is there in this. Okay, so or else other than that, what we have gone through in this truss design is design of such members, double angle arranged back to back for principal rafter and bottom tie. And one more type of design was design of a single angle section loaded through one leg only, which involved calculation of lambda E. Okay, so that will be what you need to do. And all members you have to check it for tension. Design for compression, check for tension, or design for tension, check for compression. Okay, that has to be done there. Okay, so this is the connection part what you have. So principal rafter, this is the principal rafter. What is this member? So here we have provided two ISA 60 by 60 by 5. Two ISA 60 by 60 by 5 for this principal rafter. For this bottom tie member, again it is 2 ISA 60 by 60 by 5 bottom tie. Okay, and these other members, what we have done is here for this member, single ISA 45 by 45 by 5. For this vertical member also, we have provided single angle section, which is 45 by 45 by 5. And for this member, which was of 3 meter in length, so here we have provided a single angle section of ISA 60 by 60 by 5. Okay, you'll come across this in your lab, which is there in the semester detailing lab. Okay, so there you have the detailing of this truss also. So once you design that in the lab, maybe the same truss or other truss, we will be detailing that. Okay, and at every joint you find these gusset plates. Okay, shape of gusset plate. Okay, see that they can accommodate the members which are connected over there. Okay, so this is a gusset plate what we have. For all, we have provided gusset plates of maybe 10 mm thickness over there. Yes, 10 mm thickness. Okay, so this is the arrangement of the members in the truss. Okay, half elevation, at least the half elevation has to be shown, not the full truss. You don't have to draw the full truss, half you can draw. And anyhow you are doing it in AutoCAD. If you are done with half, just you can mirror that and you will get the full truss. Okay, so this is the elevation of the truss. Now the same sections have to be shown here, details of the joints and also the sections. So three sections, one of this tie member, bottom tie member, another section, section 2 for this member, single angle section, 3 for one more single angle section. Okay, for this principal rafter and bottom tie member, the arrangement is same because of they are same angle section 60 by 60 by 5 and they are double angle section. So here the arrangement of members within the truss, how they are connected back to back to ISA 60 by 60 by 5 back to back. This is a section 1 which is taken at this bottom tie member. Okay, this is that section. This is gusset plate in between what you see. These are the boards what have been provided. So in any connection for any member, we have ensured that we are providing at least two boards, Okay. So for this member, section 2 this is our section 2 what we have here. 2 this is for this member. Okay. So here it is a single angle section, ISA 45 by 45 by 5. Okay, this is the angle which is connected with the gusset plate. You can see the gusset plate when you take this section over here. So size of gusset plate 10 mm. Similarly, section 33 is over here for this member. Okay, so this is the member what you have. ISA 60 by 60 by 5 single angle section connected with the gusset plate. Okay, this is 10 mm, not 20. This is 10 mm. Okay, so these are members cross section what have been taken at different for the different members. Okay, other than this what you have to do is you have to enlarge these connection details. Okay, so normally 2 or 3 connections have to be shown over here. So I've taken one at the support, okay, and one over here at joint B. Details at B and details at A, they have been shown over here. So what you have at this point at B, you need to just enlarge this joint with the gusset plate and show how the members are connected with the this angle section, okay, or this gusset plate, and mention what is the pitch and end distance for this connection. Okay, or else you can write it over here. If it is not possible to show it in this diagram, just write it. What is the pitch distance and end distance? That is in your lab, what you have to do. In your exam point of view, you don't have to do all this drawing. Don't go for drawing these things. For the subject theory, don't draw them. You can just show these sections when you are designing, when we have taken up the design, like we are shown over here, like individual member, how it is connected with the gusset plate, that you can show in this form. Okay, your problem will end with this part. Okay, designing the base plate and the anchor bolts, that is or I'm just clearing these connection details, the member details for you. So this drawing is not required in your theory. It is not required in your theory. So this is the arrangement of the members. Don't draw this. Don't waste your time in drawing this in your answer sheet. So details at A and B. In lab, we will again take up this, not a problem. Okay, but since we have designed the entire truss, I'm just showing you where all these members and how they are arranged. Okay, this is details at connection and details of the member. Okay, so I shared, I think, this problem already, and I want you to design this. It is of the same this truss almost, only the members have been forces are different. So some length of the member have been given here. Okay, others you have to calculate. So this is the problem what you have to solve. This is an assignment problem for you. Okay, so you have to design this roof truss, okay, with forces in each member of the truss are given in the table. Okay, the size of column is 300 by 300. You need to use M20 grade of concrete and design using M16 boards. Diameter of board is 16 mm and of class 4.6 for the connection. Also design the anchor boards. It is asked to design the anchor boards. Okay, so base plate design is just one simple step: finding the area and its thickness, mentioning the thickness. There is no design calculation you have to take up for thickness of base plate. You just adopt either 10 or 12 mm. Okay, and then design it. So length of some members have to be calculated by you. Okay, from the geometry of the truss you have to go for calculation, and these are the forces. You take these as your factored force. Okay, whatever the forces are given here, you consider them to be factored force. Okay, what change you can note here is top chord. It is said that it is only under compression. Tension force is not coming in, so you have to design it only for the compression. The bottom chord, okay, this member here, there's no compression force, only tension force is there, so you have to design only for tension. Diagonal member DFDE, which is that this DE and DF, what is it is experiencing is only compression, tension, no tension. So like that, the member forces have been mentioned. So here your job is to design for one nature of force. It is either tension or it is either compression. That is how this question has appeared. So you can try solving this. That is will be your assignment part. Okay, so that is what you need to do in design of truss. You have any difficulties in that part, anything, any part to be repeated, you can tell me. You should be thorough in design of compression member, design of tension member. Okay, what you come across other than that is calculating the strength of the bolt and deciding the connection. Any other thing? This was only the part left out here. Other than that, truss design is completed. You can take that assignment and you take up to next Saturday. Okay, I'll tell you how to submit that. You solve it and keep it ready. Okay, don't mail it immediately. You just wait. I'll inform you how it has to be submitted. Okay, the end question, what has been mentioned here, this one. Okay, this has come to you already. Design the base plate and also the anchor boards for this. The entire question has to be solved here. Are you okay with that truss design? What we covered? Because we have to move with the next part of our steel design. If truss is clear, if you have any difficulty.
No, sir.
If your answer is no, not a problem. But those who have difficulty, you can even text in your group also. You can ask here or you can text later. At any point of time, you can chat within that group. It is better you post your difficulties and problems in the group, not individually to me, because let others also come to know such problems will come across while solving. Yes, what is please share PPT. Okay, PPT I have shared. I have converted that to a PDF format, and one I have shared. This will be shared later. Okay, so go with that problem, solve it, and keep it ready. Okay, solve it clearly on on papers. Keep it ready. I'll tell you how you have to upload that. Okay, don't mail it to that earlier mail ID. That mail ID is there, still it is existing. last semester mail ID steel structure, that one, but I'll tell you this one submission. Okay, we'll finish it. Okay, let me know in this trust part if you want to have anything repeated, or we'll take one more different problem on the trust itself. Today I think we are finished with this week's class. Maybe in Monday class and all, we'll come with one more trust problem. Okay. Yes, we'll finish it over here. Okay.